Hello, I'm Suliantoro, a researcher or research center for geoinformatics. Here, I'm on behalf of our team will deliver our manuscript with the title Geographic Information System-Based Approach for Evaluating Carbon Storage in Kalimantan Basin, Indonesia. The team study comes from Research Center for Geoinformatics and Research Center for Process and Manufacturing Industry Technology, both research center under National Research and Innovation Agency. The outline of our presentation is as follows. First, introduction, then followed by method, result and discussion, and finally by conclusion. The global world has paid serious attention to the increase in carbon dioxide emission. The same incident also occurred in Indonesia. It has been recorded that the increase in emission has reached 20 times the amount of carbon emission in 2022 compared to the emission in 1970. This is largely due to the increasing use of fossil energy to meet the high energy demand. The carbon emission reduction scenario is carried out by reducing the use of fossil energy and transitioning to the use of new and renewable energy. Another effort made is to carbon capture and storage in subsurface formation, as has been done in many countries in which the carbon can be stored in coal seam, saline aquifer, geothermal, and oil and gas field in enhanced oil and gas recovery as CCUS scheme and others method. The use of CCS/CCUS technology facilitates the process of transition to new renewable energy gradually, where fossil energy sources can still be utilized while emitted carbon is captured and stored in such geological formation. CCS/CCUS program in Indonesia are still in early stage, although study has been intensively carried out since 2015. For example, the CCS/CCUS project at Merbau Gas Collection Station in South Sumatra, the CCS project in Sukawati oil field in Tuban, East Java, and the CCS project in Gundi gas field in Central Java, where all the carbon capture is to be injected into the surrounding oil and gas field. This study is focused in Kalimantan region of Republic Indonesia, where the new state capital currently is under construction. Here the location of new capital city. And in Kalimantan, we have 13 sedimentary basins with various status, from production status to unexplored basin with geological and geophysical data limited. As a new capital based on the premises of smart, green, beautiful, and sustainable city, it needs the support of various data to facilitate plan development. Moreover, fossil energy is still the main energy sources in the Kalimantan region, highlighting the necessity of establishing CCS/CCUS program for the existing power plant and industries, hence securing the new city energy and environmental basic principles. This condition could be implemented with the integrated system that includes installing carbon capture device at emission sources in power plant and industrial plant, and then transporting and storing in the geological formation according to the feasible CCS/CCUS program. Sufficient energy supply is reported to be needed in the future to support further development of the city. An estimated 3.75 gigawatt of electrical energy is needed or an additional 3.04 gigawatt over the existing electrical energy capacity. The study was performed with a set of aims focused on the classifying, weighting, and scoring using GIS in Kalimantan Basin in terms of geology, safety, infrastructure, and carbon sources, which were then used for basin ranking. The parameter will then be used to determine the reliability of basin for carbon storage, ensure the safety from potential leaks, optimize operational plan, monitor purpose, and evaluate economically. The primary output of this study is the identification of the priority basin in the Kalimantan Island for CCS-CCUS implementation. This flowchart shows how the study was conducted. In general, the study can be divided into 3 steps. The first step is literature review, data inventory, and data collection. The second step is data processing and analysis, and the third step is result discussion and conclusion. From the first step, we consider two geological carbon dioxide sources, infrastructure, and safety aspect. The study team was able to identify 21 parameters used to assess the potential of sedimentary basin as carbon storage location. In the second step, each parameter was classified into 5 classes, namely from class 1 to class 5. The classification result can be seen in Table 2. On the other hand, an analysis of the level of importance of each parameter was carried out by conducting pairwise comparison. With this process, the weight of each parameter was obtained, which can be seen on Table 3. In order to carry out spatial analysis, data management was carried out on a GIS basis, so that basin assessment could be carried out through overlapping analysis of each parameter with sedimentary basin. The result of basin assessment as carbon storage are shown in Table 4. The third stage is perform the operation of multiplying the class value of each parameter by its weight in each sedimentary basin, then getting the total value. This value is the basin potential value. By sorting the basin scores, the ranking of the basin as place for storing carbon can be determined. The result of this activity can be seen in Table 5. Table 1 shows 21 parameters and the sources from which the data were obtained. From this table, it is known that the study team collected data that related with geology, carbon dioxide sources, infrastructure, and safety aspects from various sources, ranging from government agency, previous study, and published report. Table 2 showing classification of each parameter. After obtaining 21 parameters, it deemed necessary to divide the classes of each parameter starting from 1 to 5. When the higher class, the more potential it is as a carbon storage. This classification is carried out by considering the result global scale research and adjusted to geological conditions of Indonesia. Table 3 pairwise comparison matrix of each parameter. The 21 parameters used as the basis for the assessment have different levels of importance. Therefore, it is deemed necessary to provide weight of each parameter. For this purpose, a pairwise comparison is conducted. The the parameter set as the row model and the column model. The row model compared to the column model and the value give at the crossing, its crossing. The value is between 1 up to 3, where 1 indicates that each parameter has equal value in importance. Score of 2 indicates that the criteria in the row model is slightly more important than in the column model. Score 3 indicates that the criteria in row model is more important than the criteria in the column model. This matrix shows each crossing have a value. The value is between 1 up to 3. And in the right side, we can see there is a total value. This is total value of each parameter. And then the total value, we can sum all of the value. The result is 573. And then to getting the weight of parameter, we can calculate by dividing the total value divided by the total the sum of the value. For example, for the TS, the total value is 20. Then to get the weight is 20 divided by 573. The result is 0.035. Another sample is for PM. The PM get total value 41. So the weighting is 41 divided by 573 and the result is 0.003. The total value of V is to be 1. This figure shows samples of overlapping analysis of sedimentary basin in Kalimantan with assessment parameters that carry out one by one. Figures 1 show overlapping the sources of CO2 with the basin. And the figure 2 show the overlapping between linear density and the sedimentary basin. And in figure 3 show overlapping of oil and gas infrastructure with a basin. With this overlapping analysis, value of each basin for the 21 parameters used were quickly obtained. This mapping process was carried out by referring to the parameter classification table in Table 2. Table 4, basin class for each parameters. This table shows the result of the sedimentary basin assessment in the form of pseudo values, because of each parameter is still considered to have the same level of importance. To obtain absolute value, it is necessary to carry out a multiplication operation of each parameter class with the weight of the level important. With the multiplication operation and total addition of the value obtained by sedimentary basin, the potential basin as a carbon storage location is known. Furthermore, with the operation of sorting absolute value from largest to smallest, it is known the three basins with the most potential as carbon storage location are the Kutai, Tarakan, and Barito basin. Kutai basin, the best basin for CCS/CCUS, is hydrocarbon production basin with a tectonic setting of passive margin to deltaic system, which has area about 131 km². This basin is located in the eastern part of Kalimantan basin, with its deposit having depth more than 15,000 meters. Kutai basin is Cenozoic sedimentary basin with outcrop of Paleogene rock and older rock located in the western edge of the basin. Based on seismic hazard map, Kutai Basin has the highest peak ground acceleration, around 0.3 G, where if there is an earthquake, it can reach the 7 mmEMMI scale, in which vibration is felt strongly, and therefore has the potential for moderate structural damage leading to the category of moderate to heavy level vulnerability. Nevertheless, Kutai Basin is also regarded as the center of many government-driven activities, where industry and other sectors are growing rapidly. In this basin, the new Indonesia capital city is located. Tarakan Basin is the second best basin for CCS-CCUS. Seismic hazard analysis indicate that this basin is similar to the Kutai Basin. However, in terms of intensity, seismicity is more common in the Tarakan Basin. The PGA value of the Tarakan Basin are also relatively high, with the highest being around 0.3 G. There have been earthquakes that can reach the 7 mmI scale with strong vibration, have the potential for moderate damage to building structures, and also have moderate to heavy level of vulnerability. Barito, Pasir, and Assamson Basin, based on evaluation of seismic hazard map, have the PGA value around 0.25 G, with seismicity reaching 6 mmI scale, meaning seismic activity in this area can cause light to moderate damage. The Barito Basin in addition has basement depth about 4,000 meters. Therefore, in general, the Barito, Pasir, and Asam Basin are relatively safe for CCS program. Other sedimentary basins are characterized by very limited geological and geophysical data, which implies that when they are taken into studies for their carbon storage resources, rigorous efforts are needed to secure more data through, among others, geological and geophysical survey. Finally, based on the result of this study, GIS-related approaches have proven effective in providing information for decision-making processes, as they can identify, select, and rank basins in Kalimantan for CCS-CCUS program. This finding can be used to create a priority scheme for CCS-CCUS initiative in the Kutai, Tarakan, and Barito Basin, the largest basin in Kalimantan. Additionally, this result also support the IKN program, which aim to develop a smart, green, beautiful, and sustainable city, as well as the targeted national net zero emission in 2060 goals. It is anticipated that the global trend of CCS-CCUS program will gain acceleration in the period of between years 2040 and 2060. And Indonesia has the potential to become a CCS-CCUS hub in Southeast Asia, connecting corridor with Singapore and Malaysia, utilizing the North Sumatra, Central Sumatra, and Malay Basin for permanent storage. Meanwhile, Kalimantan could be regarded and prepared as a recommended hub for the corridors for youth economic of China, Japan, Korea with Indonesia in Central and Eastern region. Conclusion: based on classification, weighting, and scoring method using GIS, Kutai, Tarakan, and Barito are the top 3 best sedimentary basins for carbon storage in Kalimantan Island. Apart from these 3 basins, the conditions sedimentary in Kalimantan in general are safe for CCS program. The basin with the lowest rank of Singkawang, Nangapinoh, Pangkalanbun Utara, and Embaluh Selatan with their sedimentary thickness of less than 1000. Therefore less favorable for CCS operation, but still have potential, even though more thorough studies required for substantial data in sufficient quantity and quality are needed. Generally, the study concludes that the Kutai, Tarakan, Barito basin, Pasir, Melawi, Asem-Asem, Ketunga, Pembuang, and Singkawang basin have the potential for carbon storage, which can accommodate carbon emission from the power plant and industrial in Kalimantan region and beyond. These carbon storage resources in Kalimantan region can certainly serve as the chain in Indonesia potential as region CCS/CCUS hub. Author thanks to the Research Center for Geoinformatics, Research Organization for Electronic and Informatics, National Research and Innovation Agency. Then to the Research Center for Process and Manufacturing Industry Technology, Research Organization of Energy and Material, National Research and Innovation Agency. The last, also thank to the RIM LPDP organization for supporting this research. Thank you very much for your attention.